Degree of a differential equation. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to recap. In our previous lesson, we focused on how to determine the order of a differential equation. As you'll remember, finding the order is quite straightforward. You simply look through the equation to identify the highest derivative present. Now that you are comfortable with identifying the order, we are going to expand our toolkit. Today, we will explore the concept of the degree. This is a new layer of analysis that provides us with even more specific information about the nature and structure of the differential equation we are working with. Definition of degree. The degree of a differential equation is simply the power, or the index, of that highest order derivative we just identified. However, there is a very important condition you must keep in mind. This definition only applies provided that the differential equation is expressed as a polynomial in its derivatives. We will dive deeper into what polynomial form actually means in the next slide, but for now, just know that the derivatives shouldn't be trapped inside other functions or raised to fractional powers. To make this easy to remember, follow this simple logic. Once you have identified the highest order derivative, which we call the order, simply look at the exponent attached to that specific derivative. That exponent and nothing else is your degree. So, it's all about finding the right derivative first, and then looking at its power. Now that we've refreshed our memory on how to find the order, let's move on to the actual definition of the degree. The essential condition, polynomial form. Now, before we jump into calculating the degree, we have to pause and check a very important prerequisite. As we mentioned in the previous slide, you can't just look at any exponent and call it the degree. First, you must ensure that the equation is a polynomial in its derivatives. What does that actually mean in practice? Well, for an equation to be considered a polynomial, all of its derivatives must be clean, meaning they are free from two specific things. First, they cannot have fractional powers. For example, if you see the first derivative of y with respect to x, all raised to the power of 1/2, that is not allowed. We need whole, positive integer exponents. Second, the derivatives cannot be trapped inside what we call transcendental functions. This means you won't find the first derivative of y with respect to x inside a sine function, or an exponential function, or a logarithm. If the derivative is the argument of a sine, and e to the power of the derivative, or a log of the derivative, the polynomial rule is broken. This leads us to our most crucial rule. If the differential equation cannot be simplified or rewritten into a polynomial form where the derivatives are free from these fractional powers and transcendental functions, then we simply cannot assign a numerical value. In such cases, we say the degree is not defined. Keep this in mind, because as we will see in the upcoming examples, this is exactly where many students run into trouble. Step-by-step guide to finding the degree. Now that we have understood the definition and the essential rules regarding polynomial forms, let's consolidate this into a practical strategy. On this slide, I have outlined a simple, 3-step guide that you can use every single time you encounter a differential equation. Step 1, identify the order. This is exactly what we practiced in our previous lesson. Your first task is to scan the entire equation and locate the highest order derivative present. Once you have found it, you can essentially ignore all the other, lower order derivatives for a moment. They won't affect your determination of the order. Step 2, check for polynomial nature. This is a crucial step that we discussed in the previous slide. Before you even think about looking for a power, you must verify that the equation is actually a polynomial in its derivatives. Look closely at the highest order derivative and all other derivatives. Are they raised to positive integer powers? And most importantly, are they free from being trapped inside transcendental functions like sine, cosine, tangent, or exponential functions? If you see a derivative inside a sine function, stop right there. The degree will not be defined. Step 3, determine the power. If, and only if, you have passed the check in step 2, you are ready for the final step. Simply look at the exponent or the power attached specifically to that highest order derivative you identified in step 1. That specific exponent is your degree. As we move into the next few slides, I will show you this exact three-step process in action through several illustrative examples, ranging from simple cases to more complex ones where the degree might not be defined. Illustrative examples. Now that we have covered the definitions and the essential rules, let's put that theory into practice with our first example, which is a very straightforward case. Take a look at this equation. The second derivative of y with respect to x, all raised to the power of 3, plus the first derivative of y with respect to x, raised to the power of 4 plus y equals 0. To solve this, we'll follow the three-step guide we just discussed. First, let's identify the order. We look for the highest derivative present in the equation. Here, we see a second derivative and a first derivative, so the highest one is the second derivative. This means our order is 2. Next, we must check the polynomial nature of the equation. As we learned in the previous slide, we need to ensure no derivatives are trapped inside functions like sine or logarithm, and no fractional powers are present. In this case, our derivatives are raised to the powers of 3 and 4, which are both positive and integers. Therefore, the equation is indeed a polynomial in its derivatives. Finally, we determine the degree. Remember, the degree is specifically the power attached to that highest order derivative we identified in step 1. Looking back at our second derivative, we can see it is raised to the power of 3. So, to summarize our result for this example, the order is 2 and the degree is 3. Keep this logic in mind, because in the next slide, I'll show you what happens when that polynomial condition is not met. Illustrative examples continued. Now, let's move on to our second example, which illustrates a very important trap you might encounter. This is a case where the degree is actually not defined. Take a look at this equation. The second derivative of y with respect to x plus the sine of the first derivative of y with respect to x equals 0. Let's break this down step by step, just like we did in the previous example. First, we identify the order. We look for the highest derivative present, which is the second derivative of y with respect to x. Therefore, the order is 2. Next, we must perform our crucial check. Is the equation in polynomial form? As we discussed in the previous slides, for a degree to exist, all derivatives must be free from transcendental functions. In this specific equation, notice that the first derivative of y with respect to x is trapped inside a sine function. Because the derivative is an argument of a trigonometric function, the equation fails the polynomial requirement. Finally, because this condition is not met, we cannot assign a power to the highest derivative. Therefore, the degree cannot be determined. So, to summarize our result, the order is 2, but the degree is not defined. Keep this in mind, because as we will see in the next example, even if the powers look simple, the presence of certain functions can change everything. Illustrative examples continued. Now, let's move on to our third example, where we can see how these concepts apply in a real-world context, specifically in physics. In fields like wave mechanics or fluid dynamics, many complex physical models are expressed using differential equations. Let's look at this simplified model of a system, represented by the equation. The third derivative of y with respect to x, all raised to the power of 1 plus x, multiplied by the first derivative of y with respect to x, all raised to the power of 2, equals 0. To find the order and degree, let's perform a breakdown just like we did in the previous examples. First, step 1, identify the order. We look for the highest derivative present. In this equation, the highest derivative is the third derivative of y with respect to x. Therefore, the order is 3. Second, step 2, check for polynomial nature. We need to ensure the derivatives aren't trapped inside functions like sine or exponents. Here, our derivatives are raised to the powers of 1 and 2, which are positive integers. Since there are no fractional powers or transcendental functions affecting the derivatives, the equation is indeed a polynomial in its derivatives. Finally, step 3, determine the degree. Now, we look specifically at the power attached to that highest order derivative we identified earlier. the power attached to the third derivative is 1. So, to summarize our result, the order is 3 and the degree is 1. Now that we've seen how to calculate these, let's pause and look at some common pitfalls where students often lose marks. Common mistakes to avoid. First, a very common error is confusing the order with the degree. It is easy to get these two mixed up when you are working quickly. Just remember this simple distinction. The order is asking the question, which derivative is the highest? Whereas the degree is asking, what is the power attached to that specific highest derivative? Keep that distinction clear in your mind. Second, be careful not to look at the wrong power. Let's look back at the first example we discussed earlier in the lesson. In that equation, we saw the term y, dx all raised to the power of 4. Now, 4 is a larger number than 3, which might tempt you to call it the degree. However, as we established, the degree is only concerned with the power of the highest order derivative. Since our highest derivative was the second derivative, and its power was 3, the degree remains 3. Don't let the other exponents distract you. Finally, please do not ignore the polynomial condition we discussed on slide 3. A frequent mistake is trying to assign a numerical degree to equations that contain things like sin of dy, dx, or e raised to the power of dy, dx. Remember, if a derivative is trapped inside a trigonometric or exponential function, the equation is no longer in polynomial form. In such cases, you must stop right there and state that the degree is not defined. Now, before we wrap up our lesson with the final summary, I want to pause and highlight some common pitfalls. I've noticed that even bright students often stumble on a few specific areas when solving these problems. Keep these 3 points in mind, and you will avoid the most common traps in this topic. Key takeaways. First, let's revisit the order. As we discussed at the very beginning, the order is simply the highest derivative present in the equation. It tells you the level of the highest derivative you are dealing with. Next, we have the degree. Remember, the degree is specifically the power, or the exponent, attached to that highest order derivative we just identified. However, there is a crucial requirement you must always check. For a degree to even exist, the equation must be expressed as a polynomial in its derivatives. This means no fractional powers and no derivatives trapped inside other functions. As a rule of thumb, keep this constraint in mind. Both the order and the degree must always be positive integers, provided they are defined. Finally, keep an eye out for the undefined case. The degree becomes undefined whenever the derivatives appear in non-polynomial forms. For example, if you see a derivative inside a natural log, or inside a sine function, or even under a square root sign, like the square root of y prime, you cannot assign a degree to that equation. All right, we have reached the end of our lesson. Before you move on to your practice problems, let's quickly recap the key takeaways from today's session to ensure everything is clear. If you can keep these distinctions clear, you'll avoid the common pitfalls we looked at earlier. Great job today.